Right. So, in the last couple of classes we had looked at structured solutions for deadlock free packet switching. Now, when we talk about structured solutions, we basically mean that for every packet we have pre-designated buffers through which the packet will be stored and forwarded. And you remember that we defined what is called a buffer graph, and the buffer graph defines the network of buffers through which the packet is stored and forwarded. Now, when we have a structured solution, the problem is that because we are limiting the routing of the packets or the storing and forwarding of the packets to specific buffers, it is not always good for varying kinds of traffic. For example, there might be certain paths in the buffer graph which is experiencing a lot of traffic leading to congestion, and though other buffers are free, we are not utilizing them, right. So, we are for specific destinations, for specific packets, we are only using a small fraction of the total number of buffers, and we are not utilizing the free buffers that might be there and may be used for routing packets. So, there are some unstructured solutions which take advantage of the fact that we need not distinguish between the pool of buffers which are available. If we can have some rules of thumb that guarantees that there will be no deadlock for accepting and forwarding packets. So, we will see some schemes like some unstructured schemes like that for deadlock free packet switching. The first one that we are going to look at is called a forward count controller. Okay. So, for a packet P, let SP be the number of hops it still has to make to its destination. Okay. So, SP is the number of hops that the packet has to make to its destination, and of course 0 is less than equal to SP less than equal to K. Now, you may wonder that how will a node know the value of SP, but then if you remember when we talked about shortest path routing, that every node was storing estimates of DUV, the distance from the present node U to a destination V. So, that distance information is sometimes available in the nodes, and through that one can determine the value of SP by looking at the destination. So, it is not necessary that the packet has to contain the SP information. By looking at the destination of the packet P, we can compute SP locally at a node, right. For a node U, FU denotes the number of free buffers in U, and given that every node has B number of buffers, where B is some constant, FU can vary from 0 to B, where FU is the number of free buffers currently in U. Now, the controller is simply specified like this, that at a node U, the controller accepts a packet P if and only if SP is less than FU. In other words, the node U will accept a packet P if the number of hops that P still has to go is less than the number of free buffers in U, right. So, it is a very simple rule of thumb. I check how many free buffers I have, I look at the destination of the packet and compute the number of hops that it still has to go, and then I see whether this figure SP is less than the number of free buffers. If so, then I accept the packet, otherwise I reject the packet. Okay. This is a simple algorithm, but the interesting thing is that this simple algorithm is a deadlock free controller. So, it guarantees that there will be no deadlock. Okay. How do we prove that? Is the algorithm clear? Yes. So, every node will accept a packet if the number of hops that the packet has to go is less than the number of current number of free buffers.
What is the analogy is like? Even if there is one free buffer, you can accept it. Why is it?
if you have only one free buffer and the packet still has 3 hops to go, then you will not accept the packet.
Why is this? There's no. It does not feel like an intuition model.
It is not intuitive. That's why the algorithm that's why we have to prove that it is deadlock free, right? But the application of the algorithm is simple, right? You just see how many hops the packet has to go, you see how many free buffers you have. If the number of hops it has to go is less than the number of free buffers, you take the packet, otherwise you tell that node that please send me later, I cannot take it now, right? We will prove that this guarantees a deadlock free packet switching policy. So, to prove it, we will use first of all, let us see what happens when all the buffers are empty. Okay. Now, there is another condition that you should note here, is that the controller is deadlock free controller provided that B is greater than K. What is B? Number of buffers in each node. What is K? The length of the longest path in the routing for routing a packet from some node to some other node, right. So, if this holds, then the controller is deadlock free controller. So, let us first see that if a node has all its B buffers free, then it will accept all packets. Why? Because SP is less than K and K is less than B as given here, right. So, SP will be less than B and we should be able to accept the packet, right. So, generation of a packet or acceptance of a packet in a node which has all empty buffers is always permitted, right. Remember, this is one of the requirements of a packet switching controller. Now, we will show that the controller is deadlock free. To show that the controller is deadlock free, we will start the proof of the fact that if B is greater than K, then the above controller is a deadlock free controller. So, the first thing that we will see is that when all buffers are free at a node U, then the node will always accept packets. Why? Because the number of free buffers is B, okay, and SP, the number of hops that a packet has to go, is less than K, right, and K is less than B. So, SP is less than B and therefore, the packet will be accepted by the controller at a node. So, that means that whenever there is a node U which has all free buffers, then it will always accept any packet. Okay, that is one of the requirements of a controller. Now, to show that it is deadlock free, we will use contradiction. So, we will use a proof by contradiction. So, to prove it, we will first say that assume that gamma is a reachable deadlock configuration. In other words, that we can reach a state where a set of packets have been deadlocked, right. Now, what we do first is that we obtain a configuration delta by applying to gamma a maximal set of store and forward moves, and of course consumption moves. Now let us understand what we mean by this. What we had in gamma was that in gamma there we already had a cyclic wait situation. So this packet was waiting for this buffer to be empty, this is waiting for some other buffer to be empty, this in turn is waiting for this buffer to be empty. Okay. Now this is a deadlock situation, but it does not mean that some of the other packets they cannot be forwarded, maybe some of them can be, right. So, and maybe there is some packet which can be consumed straight away, right. So, what we are doing is we from gamma we are checking which packets can still be forwarded, which packets can still be consumed, and we continue doing that until we reach a configuration delta where no more moves are possible. Okay. So, we obtain delta from gamma, and delta is a configuration where you cannot forward any packet, you cannot consume any packet. Is it clear what is gamma and what is delta? You can always reach delta, because after reaching gamma there are still some moves which are allowed. There are no new generations. From gamma we obtain delta by only allowing a set of store forward and consumption moves, right. So, we are not allowing new generations, no new packet is generated, only whatever packets could still be delivered, they are delivered, and the remaining configuration delta is one where no further move is possible, all the possible moves have been exhausted, right. Now in delta there is at least one packet which is not yet delivered. Why? Because in gamma there was a deadlock, so at least one packet was deadlocked, and deadlock means that it will stay, you cannot resolve the deadlock. If you could resolve the deadlock, then it is not deadlock, right. So therefore at least some packet is there in the configuration delta which is not delivered, right. Now is it understood what is the configuration delta? A configuration where no further packets can move, whichever packets are there, they are all locked, right. But we are guaranteed that at least one packet is there in the locked state, because there was a deadlock in gamma and that deadlock could not have gone away. Okay. Now let P be a packet in delta, in the configuration delta, with minimal distance to its destination. Which means, what does this mean? This means that SP is the smallest among all packets in delta. Right. So, we have chosen P to be the packet which has minimal distance to its destination. So, among all the packets I choose the one which has the minimum SP. Okay. Now, let us say that the packet P is in node U. Okay. So, let U be the node at which P resides. Now, in delta remember that none of the packets can move. So, P is stuck at node U, right, and let W be the node to which P must be forwarded. W is determined by the routing algorithm. So, what does this mean? That this is node U, the packet P is stuck somewhere here, okay, and it must be forwarded to node W, but W is not accepting P, right. So, what can we say about W? What is the number of free buffers in W? Less than SP minus 1, because the number of hops from here is SP, the number of hops from here will be SP minus 1, right. So, therefore, we know by virtue of our controller that SP minus 1 must be greater than or equal to FW, okay, and that is why W did not receive the packet. We cannot forward it to W. If it was not so, if this was less, then W would have accepted the packet, right. Okay. Now, we say that since because SP is less than equal to K, and remember that our assumption is K is less than B, okay. So, therefore, we know that FW is less than B. Why? Because FW is less than equal to SP minus 1, which is less than SP, strictly less than SP. SP minus 1 is strictly less than SP, and SP is less than equal to K, and K is less than B. So, we get FW less than B. Okay. Now, what does this mean? This means that in the configuration delta, there is at least one packet residing in W, because FW less than B means what? The number of free buffers is less than B. That means there is some packet sitting in one of these buffers. That means that there is some buffer here which is occupied, maybe one, maybe more, but non-zero. Okay. Now what we will do is, we will say that among the packets which are there in W, let Q be the most recently accepted one. So now see, W is not accepting P, right. So there must be some packet in W which was the last one that was accepted, right. Let Q be the one which was that. Among all the packets that are currently stuck in W, let Q be the one which was the most recently accepted packet. Okay. Now think of the situation when, okay, so let me just write it down for this thing, Q be the most recently accepted packet at W, okay, among those which are residing in W at delta, in the configuration delta. Okay, so that is Q. Now let F dash W denote the number of free buffers at W when Q was accepted. Right. Now Q is the most recently accepted packet at W. That means that after Q, no other packet has been accepted by W, right. So what can we, how can we compare F dash W and F W? See, there, if there were packets which were accepted by W after Q, they have also left Q. See, what is Q? It is the most recently accepted packet at W among those which are residing in W at this delta. So it doesn't mean that Q is the most recently accepted packet. It is the most recently accepted packet among those which are stuck in delta. So if any packet was received after Q, it has also left Q, right. From gamma, how did we reach delta? We only allowed forwarding and consumption. No new packets were generated. Okay. So delta is a state where the deadlock of gamma is inherited, and whichever packets could have been delivered, they have been delivered, right. Therefore delta is a situation where no other packet can be delivered. All the packets that are there in delta are, all of them are stuck. Okay. That is delta. Now what we are saying is that in delta we showed that W must have some packets, right. in delta, what is W? We first choose that among the packets in delta, which is the one which has the minimum SP. We call that packet P, the one which has minimum SP. Then we see that P, for P the next hop has to be W, but W is not accepting P. So therefore SP minus 1 is greater than or equal to FW, otherwise it would have accepted. And then by virtue of that we show that FW is less than B. That means that W has some packets stuck in delta. In delta, W has some packets which are stuck. Among those packets which are stuck in W in the configuration delta, Q is the one which is the most recently accepted, right. That means that any packet which was accepted after Q has already been delivered, right, and among the packets which are stuck could not be delivered, Q is the most recent one, right. So think of the number of buffers. So when we are looking at FW, in FW some of the other packets may also have been delivered. So compare FW and F dash W. What did we have in F dash W? That was the point when Q was accepted, okay. So F dash W number of buffers was free, Q was accepted, and Q was written in one of those free F dash W buffers. Out of those F dash W buffers, Q is sitting in one of them, right, and no packets accepted after Q are still residing in these buffers, they are not there. But some packets which were there in F dash W may have been delivered when we went to FW, when we went to this configuration delta, right. So therefore we can write that F dash W is less than or equal to FW plus 1. Right? No, that this plus 1 is because Q is occupying one of the packets, one of the free buffers in F dash W. F dash W was the number of free buffers when Q was being accepted. Then Q was written into the buffer. So what did the number of free buffers become? F dash W minus 1, right. So number of free buffers became F dash W minus 1. After that some packets got delivered and we ended up with FW, right. So F dash W minus 1 is less than or equal to FW. Remember that as packets get delivered, the number of free buffers grow, right. So F dash W minus 1 is less than or equal to FW, and therefore F dash W is less than or equal to FW plus 1, right. Now see, the packet Q was accepted in that state when F dash W was the number of free buffers, right. So we can write that SQ at this point of time, SQ was less than F dash W, otherwise the controller would not have accepted the packet, right. Now let us concatenate all of these and see what we get. We get SQ less than F dash W, which is this, right, and then we got from here that F dash W is less than or equal to FW plus 1, and then previously we had shown that SP minus 1 is greater than or equal to Fw, right. So, Fw plus 1 is less than or equal to Sp. So, this is less than or equal to Sp. So, what does this imply? This implies that Sq is less than Sp, because there is one strict inequality here, right. So, therefore, Sq is less than Sp, but then that is a contradiction, because we chose P to be the packet having the minimum Sp, right. Then how do we have another packet Q which has Sq less than Sp? That is not possible. So, it is a contradiction. So, therefore, the deadlock is not possible. All right. It's the proof is little non-intuitive, but once you go through the proof, you will realize that it does guarantee that this is a deadlock free controller, right. Is it clear? If you have a deadlock configuration gamma, you will always have a corresponding configuration delta in which no more moves are allowed. Before reaching delta, no, there is no generation. It's not actually, we are not assuming, we are saying that let delta be the configuration reached by stopping all generation and forwarding packets, right. No, why do you think that this is a physical thing that is happening? We are saying that if there is a configuration gamma, then there will be a configuration delta, reachable configuration delta, where everything is locked, right. Do you agree that it is reachable? Reachable, right. Then in that reachable configuration delta, we show there is a conflict, because if you have such a situation, so there is a conflict, so we reach a contradiction. Now, the proof says if there is a deadlock configuration gamma, then there is a reachable deadlock configuration delta in which no further moves are possible, and then we show that in delta you have a contradiction. So, delta is not possible, then gamma is also not possible, right. Now, is it all right? There is a variant of this controller called the backward count controller. So, in the backward count controller, for a packet P, let Tp be the number of hops it has made from its source. Okay. Instead of having Sp, which is the number of hops it still has to go, we use Tp, which is the number of hops it has made from its source, right. So, every time the packet makes a hop, the hop count in the packet is incremented by 1, right. So, the packet knows how many hops it has made, and the controller is, it accepts a packet P in node u if Tp is greater than k minus fu, and we assume that k, the length of the longest path in the routing graph, is known to all the nodes, and a packet P is accepted in node u if and only if Tp is greater than k minus fu. Okay. So, you will see that it's almost the same thing actually, because you might say that k minus Tp is an upper bound on the number of hops that it still has to go, right, and we are accepting the packet if fu is greater than k minus Tp, right. So, if the upper bound on the number of hops it still has to go is less than the number of free for these things. So, it automatically follows from the previous one that it will be deadlock free, right. But still you can try to see whether you can convince yourself that this is also going to be a deadlock free controller, okay. And the difference is that here it does not matter if you have an upper bound for k, it does not have to be exactly k. If you know an upper bound on k, that should also work. So, convince yourself that that will work and convince yourself that this is a deadlock free controller, okay. The proof is very similar and you can almost derive the proof for this from the proof for the other one. Another interesting variant is what is called a forward state controller. So, what we do here is that instead of just keeping the number of free buffers, we store more information like this. So, for a node u defined as a function of the state u, the state vector as j0 through jk, where j is, so this is a k plus 1 dimensional vector, where js is the number of packets p in u with sp equal to s, okay. So, j0 indicates the number of packets in u for which the number of remaining hops is 0, so they can be consumed. J1 is the number of packets which still has one hop to go. Jk is the number of packets which still has k hops to go from the node u, okay. Is this vector clear? So, at a given state in a node u, you have certain packets, you count the number of packets which has one hop to go, count the number of packets which has two hops to go, number of packets which has three hops to go, they are j1, j2, j3, etc. Okay. And then the controller accepts a packet p in node u with state this thing if for all I 0 less than equal to I less than equal to sp, I is less than b minus summation of all the packets from number of packets from which have I to k hops to go, or number of packets which has at least I hops to go, okay. Now, is this expression clear? It is again non-intuitive, but is it clear what it means when it accepts a packet? When it will accept a packet in node u, when the state is like this, provided that for all I varying from 0 through sp, this condition holds, okay. The semantics behind this, there is, I mean, what do you mean by the semantics behind this expression? This is a figure that you can compute locally, right. And the interesting thing is that if you accept packets following this rule, then you will not have deadlocks, right. Now, before we prove that this is indeed going to be the case, let us first look at this thing, that the forward state controller is more liberal than the forward count controller, okay. What was the forward count controller? We accept a packet is if sp is less than fu. The forward state controller has all these additional information. Now, this is going to be useful only if we can show that whenever the forward count controller accepts a packet, the forward state controller will also accept a packet, and in addition there are cases where the forward state controller will accept a packet, but forward count controller won't. So, if you have a more liberal controller, then you have more bandwidth, you are allowing more moves. So, things will happen faster, but at the same time we still have to guarantee that there is no deadlock, right. So, it is very important to note that the forward state controller is more liberal than the forward count controller, right. Now, how do we show that the forward state controller is more liberal? So, to prove that, so we will prove that each move allowed by FC, the forward count controller, is also allowed by the forward state controller. Okay.
So one point regarding it says that JS is the number of packets P in U, SP equal to S. What is this S for?
Here,
Yes.
JS is the number of packets P in U which has still S number of hops to go. What is SP? SP is the number of hops that P still has to go. So, your JS is the number of packets which still has S number of hops to go. Clear? Okay. Now, let us come to the proof of the fact that the every move allowed by FC is also allowed by FS. Okay. Now, assume the acceptance of P by U is allowed by FC. Okay. Then SP is less than FU, right, and what is FU? FU is the number of free packets. So, I can write that as B minus sigma of S equal to 0 through K Js. Why? I am summing up the number of packets which has 0 hops to go, 1 hops to go, 2 hops to go. So, this is the total number of packets that are residing in U. B minus that is giving me the number of free packets, number of free buffers in U. Okay. Right. So, for I less than equal to SP, right, I less than B minus S equal to I to KJS follows. Why? I am only adding more terms here, right. So, that is why that for all I less than equal to SP, right, I will have I less than B minus S equal to I to K Js, right. this implies that the move is allowed by Fs, because what is the criteria for acceptance by Fs? That for all I less than equal to this Sp, I must be less than B minus summation of I to k Js, right. So, what did we prove here? We proved that whenever a packet is accepted by the forward count controller, it is also accepted by the forward state controller, right. Now, I ask you to create an instance where the reverse is not true, that there is a move which will be allowed by the forward state controller, but will not be allowed by the forward count controller, right. And from that you should be able to conclude the whole thing, that is that this is a more liberal algorithm than the forward count controller, all right. Now, we have to prove that this forward state controller is deadlock free. The proof is very similar to the way in which SP is the number of hops that the packet P still has to go. SP has the same meaning as whatever we have started discussing from the beginning of the class, it is the same SP. Yeah, this has to be satisfied, this requirement, this has to be satisfied for all I from 0 through SP. That is the requirement, that is what the controller will check before accepting the packet, right. Now, why there is, that is not a good question to ask, why should we check this? The person who discovered this method said that look, this if you check this, then you get an algorithm which is better than the forward count algorithm, because you allow more number of moves, but it still guarantees that there is no deadlock in the system, right. Now, that is the beauty of the algorithm. Now, that has been achieved by checking this thing, right. This may not be an intuitive one, which is why you may not like it, but the fact is that it is a better one than the forward count controller, and we can prove that this is deadlock free.
Understand the concept behind it, this one. B minus the number of summation of the packets. What do we?
Now, is it clear what is J0 to Jk?
Number of packets which are have various subcounts.
Yes, in the node U, you have different packets with different destinations. You are counting the number of packets which have 1 hop to go, number of packets with 2 hops to go, number of packets with 3 hops to go. These are J1, J2, J3, etc. Right? Okay. Now, the rest of this is very simple, that when I get a packet P and my current state is this, I check for all I, for each I will check whether I is less than B minus summation of the Js from I through k. You know what these Js are, we just compute this summation, subtract it from B and check whether I is less than that.
Why do you say this is liberal, sir? It is allowing what it is allowing. What the Fs is allowing, Fc is also allowing.
Other way. Yeah. Whatever Fc is allowing, Fs is allowing. How do I prove that it is more liberal? So, there will be cases which will be allowed by Fs but not by Fc, which I have asked you to create a case like that as an exercise, right. Create a situation where forward state controller will allow a move, forward count controller will not allow that move, right. But the other thing we have already proved that whenever forward count controller allows, forward state controller will always allow, right. Okay. Otherwise, the two will become the same algorithm, right. Now, the backward the forward state controller is more liberal than the forward count controller, though it uses more amount of information, like it has to store this, maintain this state all the time, but it still is able to do it, act more liberally than the forward count controller. There is a variant of this called the backward state controller, where the state vector is different, where we say that state vector is I0 through Ik, where It is the number of packets in node U that have made T hops. So, just like we had forward count and backward count controller, we have forward state and backward state controller. In the backward state controller, the state that we have maintained is of the packets that are there in U at this point of time, we see packets which have already made 1 hop, packets which have already made 2 hops, packets which have already made 3 hops, and so on, and we count the number of packets, and those are my I0 through Ik, okay, right. And then this controller, the backward state controller, accepts a packet P in node U with state I0 through Ik if for all j Tp less than equal to j less than k. Again you check this summation, okay. Again you see this is non-intuitive, but it guarantees that the controller is deadlock free, okay. Right. The proof of this, that this is deadlock free, is very similar to the proof that the forward state controller is deadlock free, and this proof is very similar to the proof that we already studied, that is the forward count controller is deadlock free, okay. The proofs are all very similar. So, due to lack of time, we will not be able to go through the proof for the forward state controller, but I urge you to look at that from the book of Gerard Tell, okay. Now, I will conclude by making only one statement, that it was shown that Fc is more liberal than Bc, Fs is more liberal than Bs, and Bs is more liberal than Bc, okay. So, Fc more liberal than Bc, Fs more liberal than Bs, and Bs is more liberal, sorry, Bs is more, yes, this direction, more liberal than Bc, right. If you want to see the proofs of this, I can give you the references for that, okay. So, we will stop here.